Hello everyone, I am Dr. Tushar Chaudhary from Indian Institute of Information Technology, Design and Manufacturing, Jabalpur. I welcome you all to the fourth lecture session on fuel cell technology. In this module, we will going to cover fuel cell integration. By the end of this session, you will able to explain the concept of integration of fuel cell, advantages of fuel cell integration, various types of configuration of fuel cell integrated hybrid system. So, let us start with introduction. Fuel cell integration refers to the process of incorporating fuel cell technology in various application, system and industries to generate electricity, provide power or meet specific energy need. Fuel cell are electrochemical device that converts chemical energy of fuel, usually hydrogen, and oxidizing agent, usually oxygen from an air, into electricity, heat and water. They offer a clean and efficient alternative to traditional combustion based power generation and have a wide range of potential application, from transportation to stationary power generation to portable electronics and power backup units. Integrating fuel cell to these application involves designing, engineering and implementing system that harness the unique capabilities of fuel cell while addressing the technical, economic and logistic challenges. This integration can lead to reduced greenhouse gases emission, increase energy efficiency and provide energy reliability, making fuel cell as a promising solution for sustainable and clean energy future. So, therefore, this fuel cell have some advantages over here. So, advantages of fuel cell integration we are going to discuss. The integration of fuel cell into vehicle is an important technological advancement that holds a several potential benefit. Fuel cell is our electrochemical devices that converts hydrogen and oxygen into electricity and water and heat as a byproduct. When integrating to vehicle, fuel cell can offer several advantages over here. First advantage, zero emission. Fuel cell vehicle produce zero tailpipe emission, making them environmental friendly option. The only byproduct of fuel cell reaction is water vapor, reduce carbon emission and air pollution. Second, we have efficiency. The fuel cells are highly efficient in converting the chemical energy of an hydrogen into electricity, typically more efficient than internal combustion engine. This efficiency can lead to improved fuel economy and longer drive range compared to traditional gasoline or diesel vehicle. Third, we have reduced dependence on fossil fuel. Hydrogen, the primary fuel for fuel cell, can be produced from variety of sources including renewable energy and natural gas. This diversification of fuel sources can reduce dependence on fossil fuel and contributes to energy security. Fourth, we have quick refueling. Fuel cell vehicle can be refueled quickly, similar to conventional vehicle. Hydrogen refueling station can fill a tank in a matter of minute, which is faster than the charging an electric vehicle, offering convincing to driver. Fifth, we have extended driving range. Fuel cell vehicle often have longer driving range compared to battery electric vehicle. This makes them suitable for application where long distance between refueling are necessary, such as certain types of commercial vehicle. Sixth, we have high power application. Fuel cell are suitable for high power application, which can be important for heavy duty and commercial vehicle like buses, trucks and train. Seventh, we have the quiet operation. Fuel cell vehicle are quieter than internal combustion engine vehicles. The absence of engine noise contributes to quieter and more comfortable have driving experience. Eighth, we have reduced heat emission. Unlike internal combustion engine, fuel cell produce less waste heat. This can help reduce the urban heat island effect in densely populated area. Ninth, we have hydrogen production potential. Hydrogen can be produced using renewable energy sources like wind, solar and hydropower. This green hydrogen has a potential to make fuel cell vehicle even more environmental friendly. So, integration of fuel cell into various application presents have some various challenges, primarily related to technology, cost and infrastructure. There are some key challenges in fuel cell integration. Here we are going to discuss. First, we have cost and efficiency. High initial cost. Fuel cell system can be expensive to manufacture and installation, makes them less competitive with other power generation technology. Next, we have the efficiency concern. Improving the overall efficiency of the fuel cell system, including hydrogen production, storage and conversion. This crucially to reduce the operating cost and environmental impact. Second, we have the hydrogen storage and transportation. Within this hydrogen infrastructure, developing a widespread hydrogen infrastructure for production, transportation and storage is a significant challenge over here. Safely and efficiently hydrogen storage solution are still evolving. Hydrogen transportation can be costly due to its low energy density, which results in higher storage and transportation volume compares to conventional fuel. Third, we have fuel source and supply chain. Ensuring the reliable and sustainable source of hydrogen is challenging. Currently, most hydrogen production relies on natural gas reforming, which generates greenhouse gas emission. The supply chain of hydrogen and fuel cell component needs to be robust and to ensure the uninterrupted operation. Fourth, we have the durability and longevity. Fuel cell have limited lifespan and can be degraded over a time due to factors like fuel impurities, temperature fluctuation, electrode catalyst degradation. Prolonging their durability is crucial to reducing the maintenance and replacement cost. Fifth, we have the system integration control. Retrofitting of existing system or integrating fuel cell to complex industrial process can technically challenging. Developing a sophisticated control system to manage the dynamic nature of fuel cell and optimize their performance is essential. Sixth, we have fuel cell size and weight. In applications like automotive and aerospace, the size and weight of fuel cell system must be minimized to ensure the practicality and efficiency. Seventh, we have the safety and regulation. Handling and storing the hydrogen safely is a vital, as it is a highly inflammable and can pose a risk if not managed properly. Developing and implementing regulation and standards of fuel cell technology is essential to ensure the safety and compliance. Eighth, we have infrastructure development. Refueling and charging station needs to be expanded. Once we are going to expand the network of hydrogen refueling station for fuel cell vehicle and filling station for industrial application is essential for widespread adoption. Ninth, we have the market adoption and competition. Fuel cell faces competition from other clean source energy technology like battery and supercapacitor, making it challenging to gain market share. Tenth, we have the public perception and education. So, here awareness and acceptance, here two terms are very important over here, because educating the people and stakeholder about the benefits and safety of fuel cell technology is crucial for its wide adoption and acceptance. Addressing this challenge require collaborative efforts from the government, industries and research institutions to advance fuel cell technology, reduce costs and build the necessary infrastructure for this integration into various applications. Next we move towards the need of hybridization. In thermal system, which involves the transfer of heat energy from various application, can faces several issues, their impact on performance and efficiency. These issues can vary depends upon the specific type of thermal system and its application. There are some common issues in thermal system we are going to discuss. First we have heat losses, insufficient insulation. Due to this, inadequate insulation can lead to heat loss, reducing the efficiency of heat and cooling system and increases energy consumption. Second, we have the scaling and falling. Generally in heat exchanger and boiler, scaling and falling of an heat exchange surfaces can decrease heat transfer efficiency, requiring more energy to maintain desired temperature. Third, we have incomplete combustion. In combustion system, incomplete combustion in furnace, boiler, industrial burner can result in wastage of fuel, increased emission and reduced system efficiency. Fourth, we have uneven heating and cooling. In improper distribution, poor distribution of heat and cooling in HVAC system can lead to temperature variation, discomfort and inefficient operation. Fifth, we have equipment sizing. Oversized and unsized equipment leads to incorrect sizing of and heating and cooling equipment can lead to inefficiency and discomfort due to inadequate or excessive heating or cooling. Sixth, we have the control system issue. Malfunctioning or improperly configured control system can result in temperature fluctuation and inefficient system operation. Seventh, we have the steam trap failure. Steam trap failure in the industrial steam system can cause energy losses, reduce heat transfer and potential equipment damage. Eighth, we have leakage. Leakage in ductwork piping system for heating and cooling can lead to energy wastage and reduce system effectiveness. Ninth, we have the sediment buildup. Sediment built up in water heaters can reduce efficiency and increase energy consumption. 10th, we have the maintenance negligence. Falling in proper routing of maintenance and inspection can result in decreased system efficiency and increased repair cost. 11th, we have outdated technology. Obsolete equipment using outdated or inefficient equipment can significantly impact energy, performance and operational cost. 12th, we have the environmental factor like extreme weather condition. Extremely hot or cold weather can strain HVAC system, reducing their efficiency and effectiveness. 13, we have heat recovery opportunity. Missing heat recovery system, failing to capture or utilize waste heat from process can lead to loss of energy and opportunity of saving also we are going to hinder. 14th, we have mismatching load. Partial load efficiency. System not designed to match actual load requirements may run inefficiently at partial load. 15th, we have corrosion and erosion. Piping and heat exchanger damages. Corrosion and erosion can damage pipe, heat exchanger components, reducing their lifespan and efficiency. Addressing these issues oftenly require combination of regular maintenance, equipment upgradation, improve insulation, proper system design and better control system. Implementing energy efficient practices and technology can help in mitigating this challenge and optimize the performance of thermal system. Through hybridization, these issues related to system performance can be addressed effectively. Through fuel cell hybridization, issues related to lack of power, waste heat utilization, size to weight ratio, fuel compatibility, power range, etc., can be addressed perfectly. In figure 1 shows the fuel cell integration with other application which makes them hybrid thermal system. This figure has been taken from the source is mentioned over here. Now, we discuss various configuration of fuel cell integrated hybrid system. Here figure 2 shows the integration of SOFC with another fuel cell, that is PMFC. Figure 2 shows the configuration over here. The reference from where this figure has been taken is from Journal of Fuel Science and Technology. In this configuration, we have one fuel compressor, one air compressor, one condenser, one humidifier, 4 heat exchanger, 2 fuel cell, that is SOFC and PMFC, one combustion chamber, one pre-oxidizer. Fuel and air are compressed to a desired pressure which passes through an heat exchanger and enters the SOFC stack, cathode and anode side respectively. Recirculating compressed fuel support steam reforming reaction. At this point, SOFC creates some electricity, the remaining fuel can be passed for another application. Here PMFC integrated with SOFC to make system hybrid. Some of the unused fuel is cooled and again passed through high temperature water gas shift reaction and then through low temperature water gas shift reaction. These two processes can cut down carbon monoxide significantly and condenser receives rich hydrogen. To decrease exhaust gas temperature, humidity, the air coming from the compressor which is available for SOFC at cathode side. Finally, hydrogen enters the PMFC stack from anode and reacted with a humidified air at cathode side to generate electricity. Next configuration we have here in this figure, we can see the integration of fuel cell with fuel cell, gas turbine and a steam turbine. It is been taken from the source is mentioned over here and this figure is been published in Applied Thermal Engineering. In this configuration, we have one fuel compressor, one air compressor, one gas turbine, one combustion chamber, one preheater, one air heater, one heat recovery steam generator, that is HRSG. Within this we have economizer, evaporator and superheater, one pump and one steam turbine. The system uses both fuel and air recuperation utilizing gas turbine exhaust prior to steam production in HRSG for steam turbine cycle, which is single pressure. The system schematic has been shown over here in this figure. 30% fuel reforming is considered in a pre-reformer, which is achieved by mixing steam extracted from the steam turbine at desired pressure. Fuel, here we have methane, air are compressed in a fuel and air compressor respectively. Certain amount of compressed fuel is fed into SOFC anode via preheater and after reactor over here. The amount of steam extracted from the mixing with the fuel prior to its entry to preheater is taken 2.5 times of fuel flow rate. some additional amount of fuel compressed flow directly into combustor just by bypassing the fuel reformer and pre-reformer and the SOFC, which burnt along with SOFC of residue fuel and with excess air. This is done mainly to increase the power output from the gas turbine and particularly the steam turbine plant. The compressed air stream is preheated in the recuperator after it feed into SOFC cathode. Next configuration we have, the figure shows the integration of fuel cell with CHP system, that is combined heat and power system. Here in figure 4 is taken from a one source has been mentioned over here. This figure is published in Journal of Cleaner Production. In this configuration we have one fuel compressor, one air compressor, 3 heat exchanger, one water pump, one fuel cell and one afterburner. The proposed system consists of a stack of tubular solid oxide fuel cell with direct internal reforming, an afterburner and an air compressor and a fuel compressor, a water pump and a 3 recuperator. These recuperator are basically heat exchanger. The energies utilizing in building including heating, cooling and electrical load, and the proposed SOFC CHP system should be able to provide them. The heat obtained from this third recuperator, that is heat exchanger, can be supplied heating load and sanitary warm water for building in winter time. In summer, this generated heat can be used in a warm water absorption chiller to provide the cooling load and the sanitary warm water for the building. The electricity produced from the fuel cell can be utilized as a electrical load that the building needs. Next configuration we have here, this figure shows the integration of fuel cell, that is SOFC Brayton cycle with Chench cycle. Here in this figure 5 has been shown over here. This figure 5 is taken from a source and this figure is published in Journal of Power Sources. In this configuration we have one air compressor, one gas turbine, one heat exchanger, one combustion chamber, one heat recovery steam generator, that is HRSG. Chench cycle is a exhaust heat recovery cycle for specially optimize the performance of Brayton cycle. Here in this figure shows the configuration of Chench cycle combined with SOFC and Brayton cycle. The heat recovery steam generator is added for producing steam, which is injected into the gases before the turbine. The exhaust heat is utilized in HRSG, thus increases the system efficiency. Here I am talking about system energy efficiency. Because the turbine is a mass flow device, combining the steam with high temperature gases will increases the total electrical power produced. Part of steam produced in a HRSG can also be used in a steam load. Therefore, Chench cycle is a good option for following the electrical load or a steam load via controlling the steam injection. Simulation work that the addition of Chench to the pressurized SOFC Brayton improved the electrical efficiency by 1 to 3%, but Chench cycle decreases the temperature in the interior of the turbine, which permits to gain more efficiency via increasing the temperature of fuel combustion. Next configuration we are going to have here, this figure shows the integration of SOFC that uses indirect heat transfer. In figure 6, the integration of SOFC that use indirect heat transfer has been shown. This figure, the source has been mentioned over here and this figure is published in Journal of Power Sources. In this configuration we have one SOFC, that is one fuel cell, 2 heat exchanger and 2 closed power cycle. An alternative thermal coupling scheme involves indirect heat transfer as shown in this figure. The indirect thermal coupling scheme includes 2 closed cycle. Aside from SOFC cycle, the another closed cycle may be a thermal power generation plant, that is the Rankine or Brayton cycle, or TPV, that is thermo photovoltaic over here, or thermal utilizing module we can, such as the combination of CHP system with refrigeration cycle also. So, any type of power generating cycle we can include over here. The 2 cycle operation at different pressure with different working media. Often in this application of CHP and refrigeration system, the hot SOFC exhaust gas is first channeled to a air preheater, that where the heat exchanger 2 and then to heat exchanger 1. This mainly depends upon the operating pressure of the closed cycle. So, here we have discussed the last configuration over here. There are lots of other configurations are also available, but all these are in the research phase over here. So, we are going to end this session. Thank you.